smallest set of elements that everybody has one of them.
So it's not going to have to be data.
I could make a larger set that everybody has one.
I feel so much
If I
better
made it any
today
larger,
than I did a week
I
ago.
might do it in case where everybody has
I was
more
just
than
thinking
one.
of that when I got up. I was like, wow, I'm not shaking.
Now the next thing I look at is what
Feel
is the
totally relaxed,
building off
actually.
of this set. What is the smallest set?
I need to study
How many more do I have to add? So that
South Korea is
everybody has
actually
two
really,
of those
really
elements
good.
somewhere in it.
I know, and I
So
wasn't
the intersection.
I
So now I'm going to make a
It's
bigger
easy
set.
to get an A in it when you're in
Yeah.
the class, but what
And
you're
then
really
four
doing
guys.
is so
when I have to
Intersect.
actually like
BI.
It's like it's so
have
advanced
to
that
be
you
ready
can't
to
even.
answer questions.
Two
I
elements.
have. I don't know what they're going to be.
I know.
Like,
And I run that through
I can't just like
and see how many, and it turns out there
Like
are
Calc 1
5
and
of
2,
those.
I can
And
just
that's
handle
what
it.
A2 is.
Yeah. But Calc
So
3,
A2
and there's so much
is the
different stuff
cardinality of
that
this
you
set.
do too.
How many elements?
There's not really.
Okay, let's get started. So let me remind you where we were. We're talking about duality and matroids. And last time we talked about how duality works on linear matroids. And we saw that duality exactly plays the role of orthogonality if you happen to have an inner product on your vector space. If you don't have an inner product, then duality in matrix is exactly duality of subspaces. Okay? I do want to say something here that I posted on the forum, which is that during class last time I noticed that there was a better way of doing the proof than I had prepared, but I didn't want to improvise in front of you guys. So instead I just wrote it up and posted that instead as the lecture notes. And so you should see the lecture notes on the website for an easier proof of this.
Does that proof still use the inner product?
And that proof does not use the inner product. Okay.
So just the other proof more easily generalized to the case where we don't have a Euclidean vector space?
That's right. So the proof that I posted on the lecture notes on the course website generalizes more easily to non-Euclidean vector spaces. And the key I do want to write is that actually there's an easier way of describing the basis of this matroid M of V. And that I do want to make sure everybody notices. So I'll say it here. The basis of M of V. Remember last time we said the bases are some coordinates such that the projection of the vector subspace V onto those coordinates is bijective. But there's an easier way of saying that, which is that the basis of M of V are the sets, are the K sets S such that if you intersect your V with what I called X E minus S, you just get the origin. Okay? So remember, V is k-dimensional. So K is the dimension of V. Okay? So you want to know if a certain K set is a basis of the matroid M of V. All you have to do is intersect V with, this is a coordinate plane. The coordinate plane determined by the coordinates not in S. So for example, if you're going to figure out if 1, 3, 4 is a basis, let's say n is equal to 5, what you would have to do is intersect V with x2, 5, which is the plane spanned by the 2 and the 5 axes. This is a 3-dimensional space. This is a 2-dimensional space. So generically, in 5 dimensions, they intersect in the origin only. Okay. So this is an easier description of the basis of this matroid M of V. And whenever you need to look up what the bases are, then this is what you should probably use, not what I said last time. And using this description, you get an easier proof of duality. But the point is, you should see the lecture notes to see all of this. The proof is in there, okay? And so today, what I want to do is talk about duality in graphs. Okay. So, definition, a planar graph. I said this 2 classes ago. A planar graph is one that you can draw on the plane. So that vertices are points of R2 and an edge is going to be a continuous curve between the 2 vertices. You want a drawing on the plane with continuous curves so that 2 curves do not intersect if they're not supposed to. Okay? meaning
Not a vertex.
meaning only at a vertex can they intersect. So you can draw one that you can draw on the plane without intersections. The edge is intersecting. Except at the endpoints. Okay. So for example, the graph K4. Usually people will draw the graph K4 like this. You have 4 vertices, and every pair is joined. Well, that doesn't look like a good drawing because these 2 guys intersect. But you can draw this, for example, like this. There's a drawing where the edges don't intersect, and so this shows that K4 is planar. And exercise. Which we basically did 2 classes ago, is to show that K5 is not planar. So any way of drawing the graph K5 on the plane will have intersections. Okay? So that's a planar graph, and then a plane graph. It's basically a planar graph that you drew, and it's sitting in the plane. Plane graph is one that you drew on the plane. On the plane in this way.
So you're saying the first drawing of K4 is not a plane graph, even though it's isomorphic to the other one that is a plane.
Exactly. So here I have 2 pictures of graphs. This is a plane graph, and this one is not a plane graph. But K4 is a planar graph. In other words, planar depends on the combinatorics of the graph, only on the vertices and the edges. But plane is actually a picture. A plane graph is a picture of a planar graph. Okay? It's a subtle distinction, and people often confuse the two words, and that shouldn't create too much confusion.
I mean, every plane graph is planar, and every planar graph could be realized by a plane graph. So.
Right, and basically, people like to call these things planar or planar embeddings, or embeddings in the plane. So it's an embedding of a planar graph in the plane. It's a pretty empty statement, but I want you guys to see this word, embedding, which means drawing. Okay. Embedding or drawing, same word. Okay. Now, so here's an observation. If you draw a plane graph, you get something like this. There's a clear notion of regions of this, right? A plane graph is going to divide your plane into different regions. Into the regions, which I'm going to call faces. The reason for this, if you know a little bit of topology, is the Jordan curve theorem that says if you draw a continuous loop in the plane, then that's going to separate the plane into an inside and an outside. Okay? But if you don't know topology, then this is going to be obvious to you. A lot of topology is devoted to making formal, to giving proofs of things that seem obvious to you. Okay? But this happens to any plane graph, and so what I'm going to do is I'm going to define the dual graph of a plane graph. Okay. Question?
When you move on to more graph, I'm not sure of, can you give an example of how planar graph and plane graph at the same time? So I can tell the difference.
I'm sorry, say that again?
Okay, I don't really understand what's different between planar graph and plane graph. Is there any graph I can look at and able to tell?
Well, the thing is that, so the question is this: what is the difference between a plane graph and a planar graph? Do you want to take a stab at that?
The planar graph hasn't yet been drawn. It's one that could be. The plane graph is the drawing of it in the plane. They're the same graph. So I can say, theoretically, K4 is a planar graph. It's a graph that can be drawn in the plane. Can. There it is. It's the triangle over there. So it can be drawn in the plane. That little drawing of the triangle that you did right there is the plane graph of K4.
A plane graph.
A plane graph of K4. So it's the difference between a theoretical graph that could be drawn on the plane and the actual drawing of that graph on the plane. It's the difference between the two words.
And maybe one thing that I should say is what is a graph? Really, I haven't really defined the graph. What is the graph K4? The graph K4 is a collection of vertices that I'm going to call A, B, C, and D, and a collection of edges, which are pairs of vertices. AB, AC, AD, BC, BD, CD. This is a graph, and if you want to define a graph, you specify what the vertices are, what the edges are. And so a graph is not really a drawing. People like to draw them because that way they're easier to visualize, but the official definition of a graph, the mathematical definition of a graph, is a vertex set and an edge set, where each edge is a pair of vertices. Okay? And so this is really the distinction. This guy right here, this combinatorial object, is a planar graph because I can draw it as a plane graph. Okay.
So all that, sorry, go ahead.
So the one you drew before that, the intersect, that example you give to us, that's not a planar graph because they cannot intersect.
Right, so here are two drawings of K4. K4 is an abstract combinatorial object. K4 is not a drawing. And here are two depictions of what of K4. And now these depictions are physical objects sitting in the plane. This one is not planar because there's an intersection. And this one is, sorry, this one is not plane.
That's not a plane.
Yeah.
Yeah.
That one's a.
And this one is plane.
Yeah.
In other words, the adjective plane refers to drawings.
Yeah.
So K4 is a planar graph
Yes.
because it can be drawn on the plane. There are two pictures of K4. The one on the left is not a plane graph because stuff intersects, but the one on the right is a plane graph because nothing intersects.
So can both of them be planar graphs then?
So, no.
They are both the same graph, and it is a planar graph.
So a plane.
These are two physical representations of the same graph. A graph is not a picture. A graph is this collection of a set and another set. These are two pictures. This is a plane picture. This is a non-plane picture. And because there is a plane picture, I call this a planar graph.
And all the vertices have to be connected.
In a complete graph, K4.
So this is the graph K4. In general, if I want to define some other graph, then I define some vertices and some edges.
Oh, okay. So that one could be planar, but it's not, just not called K whatever, how many vertices.
Oh yeah.
Right.
Yeah.
Kn means you have n vertices and an edge between every picture.
Okay. So
Thanks for asking that question. It makes sense.
Federico, this is an if and only if.
what is an if and only if?
Have we
Definition, obviously. That, it's planar if there's an associated plane graph. There's an associated plane graph. The definition.
Right. I mean, these are basically the same definition, and this is a combinatorial version, and this is a kind of the topological version. I mean, this is why people just often will call them plane or planar, and they will even confuse the definitions because we like to think of graphs, which are combinatorial things, as pictures. You have to be a little bit careful here, but they're basically the same definition. Now, to a plane graph, in other words, to a drawing, I'm going to associate a dual plane graph. So let's say G is a plane graph. In other words, a picture. I'm going to define a dual plane graph. Which I'm going to denote G star. Okay? And this is one of these definitions that is easier understood in an example than in words. So let me draw an example and then we'll say it in words. Let's say that my graph is this one. Okay, there's a graph. It's a plane graph because I'm considering this as a drawing on the plane. There's vertices and there's edges. Each edge is a continuous curve. What I'm going to do now is basically what I did with the map last time. I'm going to put a blue. Actually, let me pick a color that's even more different than blue. I brought the whole kit today. So let me put a red vertex inside each face. Okay, so here's one, Here's another one. Here's another one. Here's another one. Another one. Another one. And another one. Am I done? No, there's another face, which is the outside face, okay, which I'm going to draw here. Okay. So let's say that G has vertices V, edges E, and faces F. My new plane graph G star is going to have as vertices basically the faces of this guy. Okay? So I'm going to call this F star, and these are going to be the vertices of my graph G star. For the edges, I'm going to say whenever I have an black edge, that black edge has two sides. And those sides are two regions. And so I'm going to join those two red regions. For example, here's a black edge. It joins these two regions. And so this black edge separates these two regions. And so I'm going to join those two regions with a red edge. Okay. So for each black edge, I'm going to just draw an edge crossing it. Okay. And I get a picture like this. Am I done?
No. You need something from the top.
I'm not done because there's this edge. It's always. Maybe now you can see why I chose this funny shape so that I only have one weird edge like this. So for each edge in E, I'm going to get another edge in E star, which basically crosses it. Okay. So what is G star? Vertices of G star are,
Faces of G.
let me use the same notation that I'm going to use for my proofs. So if F is a face of G, then I'm going to get a vertex of G star, which I'm going to call F star. Okay. For each edge of G, I'm going to get an edge E star. And how do I define it? Well, if the edge E separates faces F and G, then that means I have a vertex F star, a vertex G star, and I'm going to join them, and that's going to be the edge E star. Okay.
Could you review again, how did you decide which of the red vertices you were going to connect?
So I connect two vertices if they're neighboring countries. For example, if I think of the black thing as a drawing of a map, then these two are neighboring countries, and this is the border. And so I join the two neighboring countries by crossing that border.
That little red dot, the top red one, that doesn't get joined? Those aren't neighboring countries?
So for example, why am I not joining this vertex and this vertex? Because
It doesn't cross an edge.
because there's no edge between those two countries, you see? Those two countries cross at a vertex. But I only put a red edge whenever I see a black edge.
But there are two ages in this point. That red dot and the dot dot.
Right.
There's two.
There are two ages in this point, right?
Two
I mean,
edges.
if I try not to look at the vertices in this point, if I see there are two ages.
Oh, I see your question. So I think I see your question. So for example, if I have a situation like this, if this is my graph, G, then what am I going to do? I have to assign a vertex in each region. So there we go, vertex, 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 vertex. And for each black edge, I have to assign a red edge. So for this black edge, I assign this one. For this black edge, I assign this one. But now, for this black edge, I go around like this. And for this black edge, I go around like this. So in other words, here I have two countries that have two different borders between them. And therefore, I need to join them twice. So the number of red edges between two countries is equal to the number of different borders between them. Okay.
You could sort of think about it as border crossings. And
Before I do this, let me just finish the picture so that, because I'm not finished, right? I still have to join this guy and this guy. And this is my graph G star. Okay. So what was that again?
I was just thinking, you can think of it as border crossings where you can't cross through a vertex. In other words, like that's not a legitimate border crossing. You're going across one of these borders, but like you don't connect to the center one because that's not really a border, that vertex.
That's right.
So 3 countries at the same time.
That's right. So each red edge is a border crossing. But let's say that you're not allowed to cross from a border to another, from a country to another one, and as there's a segment of a border, you can't cross to the corner of 3 countries.
So the rule is saying that you can only cross one block, you cannot cross 2 blocks.
Right. Okay. Okay. And any other questions about this construction? Chris?
If you have a loop, how do we?
What if, for example, I think instead of making formal definitions, the easiest way to understand is just to do kind of the strange example. So what do I do in this example?
Same thing.
And actually, let's even add another connected component. So what do? Well, again, I put a vertex in each region. Notice let me just put this red vertex, which is the outside face. Okay. So now, here's a black edge separating these 2 regions. Here's a black edge separating these 2 regions. Here's a black edge separating these 2. Here's a black edge separating these 2. Am I done? No, because this black edge is separating this one and this one. But that's really the same region.
Yeah.
So what do? Well, I do this. because I need to draw an edge that goes, I mean, this is a black edge separating 2 countries, which happen to be the same country. So I need to draw an edge from that country to itself that only crosses the black edge. So that's what I have to do. Okay. Stare at these pictures for a while if they don't make sense right away. But this is what you have to do. Okay? Now, the one thing I'll say is that this E star is an edge of G star that crosses only E. E only. Okay. So this is my definition to go from a graph to its dual. Okay. Now, if you look at this table that I'm starting to draw over here, there's certainly something missing here, which is, what are the faces of G star? Well, if you just stare at this picture, you see that each face of the red map corresponds exactly to a vertex of the black map. For example, here's a red face, and there's exactly one black vertex inside it. here's a red face, this triangle, there's exactly one vertex inside. Each red face contains exactly one vertex. Okay? And that makes sense because a face is just going around a vertex from this country to this country to this country. So the faces of G star exactly correspond to the vertices of G.
Face it. Whoa, something.
Sorry. So the faces of G star correspond to the vertices of G. Okay? So for each face of G, I have a vertex of G star. For each edge of G, I have an edge of G star. And for each V vertex of G, I have a V star, which is a face of G star. Okay. So that's my definition to go from G to G star. Okay. So maybe you can guess the first statement that I want to say about this notion of duality. Which is that what's the dual map of the red map? Almost by definition, it's the black one. Right? So if the dual of G star is G. In other words, if you take a map, if you take a graph, take its dual, and then take the dual of that, G will serve you. Let me change the wording a little bit because, as you can see, there's different ways of drawing this red map, right? I mean, if I draw a black graph, there's different ways in which we can draw the red graph. For example, here, going from the black to the red, I had several options. For example, the red guy could have looped around this way, or it could have looped around this way. So there's several possibilities for what this dual could be. So what I'm saying really is that if G star is a dual of G, then G is a dual of G star.
So you could also say isomorphic. That's what you're saying. Okay.
No, I'm saying if a graph G star serves as a dual of G,
Okay.
then G serves as a dual of G star. Okay. I need an assumption here.
Planar.
I need another assumption.
Already
Which-
drawn. I guess
No,
that's
because
the same,
plane
but
graph
plane-
means that it is drawn. Okay. There's another assumption that I need, which might not be immediately obvious, but it's that he has to be connected.
Yeah, I was thinking that, but then we did one that wasn't connected, so then I was not
No, it
thinking.
is connected.
But it's the dual is not.
The dual.
So
Well, oh yeah, the dual. Yeah.
so let's see why this fails us. So
So the point is you can.
So
still-
first, let me say something. Let me say proof. Just stare at the picture long enough and you'll see it. And you can formalize it. Stare at the picture long enough.
Staple into a blanket.
And then and then formalize what you see, and then tell us what you see. I mean, this is really the proof. There's nothing to it except for staring, understanding, and translating into mathematical language. Okay? But I do want to see why this fails for non-connected graphs. So why connected? Let's take one that's not connected. For example, this one. There's G. Okay. So what does G star look like? You're going to have a vertex inside each one of these little triangles, a vertex inside this triangle, and an outside vertex. Okay. So like this. Then you see, I'm putting them here, right? Here, 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 and here. So now you see, well, let me just draw it over here. So I need to draw this edge, and this edge, right? So this one, and this one. And then here I have 3 edges separating this country from the outside country. So I need one here, and one here. So that's my dual graph. Okay.
So we can already say the dual of, because you can define the dual of a not connected graph, and so the dual of any planar graph is connected.
So that's the first thing that's true.
Yeah.
Is that if you start with any graph, connected or not, if you start with any plane graph, the dual is connected.
And then you get a subgraph.
Let's see what happens when you go and take the dual of this guy. G star star. Maybe I'll use a different color because I think this one is not going to show very well. G star star. So vertex here, vertex here, vertex here, vertex here, here, and here. Yeah?
When you choose the vertex outside the pictures, how do you know where to put that?
I don't know.
Doesn't matter.
So the question is, how do I know where to put this outside vertex? Do I put it here? Do I put it here? Do I put it in the student center? Those are all perfectly good options. And that's why I say that there are different possible duals, because you could choose any point outside in the outside region. That works. Okay. Okay.
Is it true that theoretically, though, you could kind of squish it around to make it look like that?
That's a very good question.
Okay.
It's a very good question, and I won't address it just yet. So the question is really how different are these drawings? Is there some equivalence between them? And if you know some topology, you know this is a topological question, and one that we might get into later on, but not right now. Well, how do I already know that I'm not going to get back G? Because I just told you that the dual of anything is connected. So this is going to be connected, and G is not connected. How does it look? Well, it looks like this. Okay. Now, if you let me take this piece of the graph and degenerate it for you. So I'm just going to draw it like this. That's this piece. And then this guy is kind of hanging out over here.
Right. It identified two of the vertices.
So you see what happened when I went to the dual and then to the dual of the dual? These two things kind of, it looks kind of similar, it's just that they got glued together. Why ponder that question? But so these two are similar, but they're not exactly the same graph. This guy got connected in a way to BG star star.
I thought it was going to get connected either.
I mean, of course, it could have been connected in different ways if this drawing was different.
I thought you might just get an edge all of a sudden somehow connect. Like, I was just thinking about it real quick. That's not what happened. It actually.
You can't get an extra edge because the edges correspond to edges.
That's true. So it did somehow.
So it just glues vertices in some way. Okay, but the point is when G is connected, this doesn't happen. Okay. Again, this is deep down a topological question. I mean, well, this is deep down a topological question, but
So Federico, since the dual is connected, the dual is connected, take the dual to dual to dual, you're going to get back to dual, right?
right. So it is true that G star 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 is equal to G star for any.
For every fucking graph.
Okay. Maybe, wondering if I should try to squeeze the proofs, but maybe I won't squeeze the proof of this. I mean, of course, the point is that Matroid duality is going to correspond to this duality. And we'll see that next time, but maybe what I will explain to you now is where this notion of duality comes from. Okay. Why did people bother defining this duality in graphs? So this brings us to some more cultura general. Something else that you might find in a crossword puzzle. Cultura general in graph theory. No, this is important enough that any student of mathematics should know about this. What's this dual thing about? I mean, why did people come up with this? This comes up from a conjecture that was open for, I think, over 100 years. But probably you've heard of it before, called the Four Color conjecture. The Four Color conjecture says that given any map, well, it says any map can be colored with four colors. Using four colors. But of course, you don't want neighboring countries in a map to have the same color because you couldn't tell them apart. So that neighboring countries have different colors. So let's talk about the map of the Americas again. Actually, North America is pretty boring when it comes to map coloring, so let me ignore that. And you already saw that I don't know the geography of Central America so well, so we just focus on South America, which I actually kind of know how to draw. So South America looks kind of like this. Colombia's up here. It's the one I can draw the best. Brazil is over here, and it looks like a smaller version of South America, kind of. Here there's Venezuela. There's 3 countries that you might have never heard of, which are the 3 Guyanas. And this is an honest border between Colombia and Brazil. Then over here is Peru. It's hugging Ecuador. Chile is long like this. Argentina is very big. It's like this. Argentina, Chile. Uruguay is over here. Paraguay is over here. This is Bolivia. Brazil, Colombia, Venezuela, Guyana 1, Guyana 2, Guyana 3. French Guyana, English Guyana, Dutch Guyana. Okay? I'm sorry? That's a good question. I think they don't. No, they do actually. They had a big fight over this. Bolivia used to have a coast. And now they don't because of Chile. That's right. So now the question is, okay, I want to color South America with colors. But I don't want neighboring countries to have the same color. Now, are 3 colors enough? You have to stare at this for a second. This is not an immediate question, but why are 3 colors not enough?
Well, if you just use the Guianas and then put in Brazil, you're already in.
No, but for example, this could be
You're right.
blue, red, yellow, red. But if you focus on this part of the map, you see that you have 4 countries that are all neighbors with each other. Yeah? These are all neighbors with each other. So no 2 of them can have the same color. So you need 4 colors. Okay? So 3 colors are not enough. And so this kid noticed in the 1854, 52, that he could always do this. This is a conjecture of Guthrie in 1852. And he was just a student who was coloring maps, having fun with it. And he conjectured this, that any map could be colored in this way. And he asked his teacher, why is this true? I should say any map where the countries are connected. In other words, this theorem does not apply to the US because the US is not connected. There's mainland US, and then there's Alaska up there, Hawaii over there, Puerto Rico, all over the place. You guys know that.
That actually makes it easier because those guys are.
But anyway, so this was a 4-color conjecture, and people thought, okay, this is kind of an easy question. There should be an easy answer to this. And it's turned out to be an incredibly hard question. It took almost 40 years until anybody did anything with this. In 1890, people proved that 5 colors were enough. 5-color theorem. This one you can actually read the proof. It's a couple of pages. It says due to, I'm not sure how you say this. He would maybe. Okay. And people thought, okay, if we know how to do the 5-color theorem, we should be able to do the 4-color theorem. And it took until some of us were alive when this happened. 1976, people finally settled this 4-color theorem. And these were 2 guys, Apple and Haken.
Wasn't there a lot of dispute though over whether they really solved it or not?
But then, right, so people aren't very happy with this proof to this day, because first of all, this paper is like 500 pages long. And it takes 500 pages to say, okay, if a map doesn't satisfy the Four Color Theorem, then it must be one of these 1900 maps. And then we have to check those one by one. And so they had to ask a computer to color these humongous maps because it was too much work for them. So literally, there were 1936 cases to check.
So they were able to prove it except for those?
So basically, they said, if it's true for these 1936 cases, then it's true for any graph. So it took 500 pages of arguments to do that. And you can imagine that if the outcome of 500 pages is a collection of 1936 graphs, and this is a pretty messy thing that people don't want to read, really.
Yeah.
And so for a long time, people thought, is this really a proof? Can't we do better? And we can do a little bit better, but we still don't have a proof that says, okay, this is really the reason. All the proofs are kind of computer-assisted at the moment. Now it's shorter, there's fewer cases, but still, I mean, it's a whole book to understand this theorem. The point is that if you look at the dual graph, then this becomes a question about graphs. And people thought that this was the tool they needed to settle this conjecture. Okay.
You're missing Chile and Peru.
Chile and Peru.
Or whatever.
Yeah.
Colombia as well.
And
Peru. Yeah.
and people thought, okay, maybe by doing it this way, what I'm doing is coloring the vertices of the graph of my orange graph G star. And they thought, okay, now this is a vertex coloring problem, and maybe we have some tools to do that. And actually, a lot of matroid theory was developed because people thought maybe this is a theorem about matroids. And maybe the way to prove the Four Color Theorem is using matroid theory. Some people still think this, but it's been many, many years and still no proof. Okay. But this is kind of the historical perspective behind this construction of duality. And because it fits so well with matroid duality, people thought, okay, now we have tools, hopefully, to attack this question. Okay.